Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 13, Lesson 5 on Making Inferences, Day 2. Now it's really helpful if you were with us for Day 1, and in Day 1 we really looked at sample means. So let's see what we're going to be doing in Day 2. Alright, now the likelihood of a sample proportion. In our previous lesson, we used results of statistical simulations to determine how likely it was that a given sample mean could plausibly have been drawn from a population with a particular mean and standard deviation. In this lesson, we will determine how likely it is that a given sample proportion, and when I say sample proportion, you can think of as a percentage that falls into some category, right? That a given sample proportion would be drawn from a population with a specific population proportion. All right, so let's take a look at exercise number 1 so you can understand what I'm talking about. It is estimated that 78% of all Americans have brown eyes. By the way, that is a realistic percent. Ms. Amati finds that for her 50 students, 86% have brown eyes. She wants to determine whether the percentage for her students is unusual, whatever that means. She runs a statistical simulation 1,000 times, where a random sample of 50 is drawn from a population with a proportion of 0.78 having brown eyes. For each randomly drawn sample, the sample proportion is found. The distribution of these 1,000 simulated sample proportions is shown below. Now again, before we even get into letter A, I want to make sure that you understand what's going on here. All right. Now, if you were with me for day 1 of inferential statistics, or making inferences day 1, then you already probably know where I'm going with this. But again, I want to take my time to really explain it because this is like nothing you've ever done before, except for in the last lesson. All right. The idea is very, very simple this time, right? We've got a computer, right? And a computer says, all right, I've got a population out there where 78% or a proportion of 0.78 have brown eyes. And what I'm going to do is I'm going to randomly pick 50 from that population, all right? And I'm going to count how many of those 50 have brown eyes. I'm going to then divide by 50 and I'm going to come up with a sample proportion. Now, we kind of expect that sample proportion to be pretty close to 78%, but I could just get unlucky and I could get like a sample proportion of where maybe only 50% of the 50 people had brown eyes, or maybe I got kind of lucky on the other direction and every one of the 50 that I pulled out of that simulation had brown eyes, so maybe I had a proportion of 1.0. All right, and by the way, unlike our simulations that we talked about in our last lesson, this, I can actually explain exactly how we would do it, right? Computers can generate random numbers easily, all right? So what you would do is you just have a computer generate a random number between 0 and 1, okay, which would be a decimal. And if that decimal was 0.78 or below, so between 0 and 0.78, we would count that number as being a person that had brown eyes. And if the number generated was 0.79 up to 1, we would count that as a person that didn't have brown eyes. So it would be very easy to generate 50 random numbers and just count the numbers that are from 0 to 0.78. Those are the brown-eyed people. And then 0.79 to 1, those are the non-brown-eyed people. And then come up with a sample proportion. Now, we do that 1,000 times. So we draw 1,000 samples of size 50 from this population having 0.78, having brown eyes, and this is the distribution of those sample proportions. And there's a ton of them because I've done it 1,000 times, all right? So let's take a look now at letter A. How does the mean of the simulated sample proportions compare to the population proportion? Now again, always the statistics for my simulations are going to be kind of shown somewhere on my graph. So here I see that the mean, the average of all my simulated sample proportions was 0.781 and the standard deviation was 0.059. And I know those are pretty small. Let's go back to the graph for a second so you can really see them. I think that's a little bit easier to see, hopefully, right? The mean was 0.781, the standard deviation 0.059. So now, letter A, how does the mean of the simulated sample proportions compare to the mean, compared to the population proportion of 0.78? Pause the video now and go ahead and make a judgment call. Well, it's all but equal, right? The mean of the simulated sample proportions is almost exactly the same as the population proportion. That's very similar to what we did in our last lesson, where we saw that the mean of the sample means was basically the same as the population mean. Here, the average of our simulated proportions, of our sample proportions, as long as we do a ton of them, and 1,000 is quite a few, that mean will be basically identical to whatever our population proportion is. And that kind of makes sense because we expect most of the samples to have about 78% of the sample having brown eyes. All right, let's take a look at letter B. Does the distribution of sample proportions appear to be normally distributed? All right, well, pause the video now and make a call on that and give an explanation for why you think it is or isn't normally distributed. All right, well, I'm going to say, yeah, most certainly, right? And again, if I superimpose a normal curve on that, boy, does that fit that well, right? It really does. And so the answer is yes, it is symmetric about its mean, and it has a bell-shaped curve. And what's really cool is that in theory, if I didn't do the simulation 1,000 times, let's say I did it 1,000,000 times, 1,000,000,000 times, it's a computer doing this, why not? Let's let it work all night. We can make it do as many simulations as we want. It would be a perfect normal distribution. The only reason it doesn't look perfect right now is because I only did 1,000 simulations instead of 1,000,000, 1,000,000,000, whatever. But yeah, it's definitely a normal curve. Now let's take a look at letter C. Could the proportion of Ms. Amati's students occur due to sampling variability in the overall population? Show where her class's proportion falls in the distribution. All right, so we talk about the overall proportion being P equals 0.78. When we talk about a sample proportion, we often put like a little weird thing on top of it like this. We often call it P hat. All right, I know that's kind of funny, but the sample proportion P hat is 0.86. Does that occur somewhere in here? If so, see if you can find it. Oh, you bet it does, right? And it occurs pretty easily, right about there. So, it definitely can. You bet it does. And again, keep in mind what that says. This is really important, right? That says that if I'm just randomly taking groups of 50 from a population that has 78% of its population with brown eyes, I can definitely get a sample where 86% of the people have brown eyes. It's right there, right? Now, the question is, just like in our last lesson with sample means, is that far enough away from the center of the distribution to say, well, that's kind of unusual? Right? That's weird. For instance, if she had a class where only 22% of the people had brown eyes, which would be way down here, right? This thing starts at 60%. It'd be way down here. You'd be like, well, there's something strange going on here, right? For some reason, she lives in an area where not very many people have brown eyes for whatever reason, right? So let's now talk about letter D. Construct the 95% interval for the proportions based on the mean of the simulation and its standard deviation. All right, well again, this is right from what we did in our last lesson, except in our last lesson we took the mean of our simulated samples, right, sample means, and the standard deviation of our sample means, and we added 2 of them and we subtracted 2 of them. Here we're going to do exactly the same thing. So let's go through this together, right? What we'll do is we will take our 0.781, this number, and we will subtract 2 of our standard deviations, 0.059, and we'll get our lower bound. Then we'll take 0.781 and we'll add 2 of our standard deviations. Remember, according to the normal distribution, right? 2 standard deviations above and below encapsulates 95% of all the values. This will be 0.663. This will be 0.899. All right, so there's our interval. Okay, so 95% of all of our simulated sample proportions are going to fall between 0.663 and 0.899. Awesome. So let's now take a look at letter E. Does the proportion for Ms. Amati's students fall in the interval to D? What does this tell you about why it is plausible that this sample occurred due to sampling variability? All right, so let's take a look. First, does her proportion fall within this interval? That should be an easy question to answer. Pause the video and take a shot at that yes/no answer. And the answer is absolutely, right? 0.86 is greater than 0.663 and less than 0.899, right? And it's really cool. We can definitely visualize it, right? So there is my plausible interval. In other words, any kind of proportion that's between that value and that value could plausibly have just happened by sampling variability, right? So the answer there is most certainly yes. And there it is. Since Ms. Amati's class had a proportion that fell within the 95% interval, there is a reasonable chance that it occurred simply due to sampling variability and not due to induced variability, right? In other words, there's no reason to conclude that somehow Ms. Amati's students come from an area where people just generally have a higher percentage of people with brown eyes, right? There's just no reason to conclude that because it falls within this interval. Had she had, let's say, 95% of her students having brown eyes, then we would say, oh, wait a second. That isn't likely to have happened by chance alone, by sampling variability alone. But since it certainly does fall, and let me put yes down here since that really answers the first part of the question, right? Since it does fall within that interval, we can say, hey, it could have just happened due to sampling variability, and therefore there's really nothing unusual about that proportion. Okay, so let's talk about the 95% interval test again. Just as with sample means, the variability we see in sample proportions could either be due to sampling variability, like what we saw in the last situation, or due to induced variability, right? Something that's actually different about the population that we took our sample from versus the population we're comparing it to. Now, when compared to a population, we will still use the following test. Let's take a look at our 95% interval test again. If a sample has a proportion that falls within 2 standard deviations of the simulation mean proportion, then it is plausible, i.e. possible, that the sample came from the population used to generate the simulation. If it falls outside of this interval, then we would say that the sample proportion is unlikely to occur based on chance alone, and it is likely the result of induced variability. So yet again, we go all the way back to our first lesson in our statistics unit. There are 2 major types of variability that we're concerned with. Sampling variability, which just occurs because if I take random samples, those random samples will give me different means and different proportions, depending on which one I'm kind of concerned with, right? Sampling variability. And then there's induced variability. Variability that occurs because for some reason, right, the sample that I took has a higher mean than the population, right, that we're kind of concerned with, or a higher proportion than the population we're comparing it to, right? And we use that 95% interval test to say, well, if the proportion that we got is way out there at the tails, then something strange is going on there, right? Something is different. So let's take a look at another example of this in exercise number 2. It is estimated that approximately 25.4% of all American households have at least one cat as a pet. Paloma's Pet Palace asks 40 customers leaving their store if their household has a cat, and finds that 18 of them have at least one cat. Letter A. What is the proportion for the sample that Paloma's Pet Palace took? All right, so get your sample proportion here. Figure out what P hat is, right? That's going to be 18 divided by 40. And why don't you go ahead and calculate that out as a decimal Pause the video now and figure that out. All right, well, that happens to be 0.45, right? Or if you want to think about it as a percent, 45%. Now again, maybe that's not unusual, kind of like in our last problem. Maybe like in the situation where Ms. Amati was trying to figure out whether it was unusual for 86% of her students to have brown eyes. Maybe that's not unusual. Maybe that's just pure sampling error, or sampling variability. Let's take a look at letter B. Is that sample proportion from A within the range of simulated proportions? Draw an arrow to where it would land on the graph. All right, well, take a look. Does this lie within the entire range of the simulation, right? So we're now simulating, a situation where we're going to take 40 customers or 40 simulation values from a population that's got a mean of 0.254, right? A proportion of 0.254, hard for me to say that, and we're getting this distribution of sample proportions. Does that 0.45 fall within there? Pause the video now and consider that. Yeah, and it definitely does, right? Now don't get me wrong, it kind of falls way out there, but notice we got a simulation that's even larger than that, So the answer is yes. Whoops. Right? Now again, what that says, right? Be very clear. What it says, the fact that we've got that proportion way out there, is it says to us that it is possible, right, that we could just randomly pick 40 people from a population where there's only 25.3% of people owning cats, right? We could do that, and we could still get a sample from that by just pure sampling variability where 45% had a cat, okay? That sounds funny the more I say it. Letter C. Is it plausible that the sample proportion for palomas was drawn randomly from a population with a proportion of 0.254? Justify your yes/no answer. All right, so what I'd like you to do is I'd like you to create the 95% confidence interval centered on this mean, all right? Take that 0.253, I know that that's not exactly the 0.254, but we're always going to use our simulation results. So take that 0.253, subtract 2 of these standard deviations from it, add 2 of these two standard deviations from it, and see whether our sample proportion falls within that. If it does, then it's plausible that that's just pure blind luck, just a sampling, variability. If it doesn't, then we'll discuss. Pause the video now. All right, so here we go, right? So we're going to take our mean of 0.253, and we're going to subtract off 2 of those standard deviations, and we're going to get 0.117. All right, then we'll take our mean, 0.253, and we'll add 2 of those standard deviations, and we'll get 0.389, right? And notice, right, that 0.45 does not fall within that interval. So, is it plausible? The answer is it is not plausible because it does not fall within the 95% interval. Now, if you like a nice turn of phrase, right? It is possible. It's possible, but it's not plausible, right? Or better yet, it's not likely. All right. Now statisticians tend to talk about plausibility and non-plausibility, right? So again, it's definitely plausible. We did a simulation, right? A ton of these simulations. In fact, I did 500 of them, and I got one one of them that I drew out of a population with 0.254 as the population proportion, right? This sample of 40, that got me actually a proportion that was bigger than 0.45. But, right, because it doesn't fall within 2 standard deviations of the simulation mean, we say that it is not plausible, right? It's not likely to have actually come from that population. So let's take a look at letter D. Based on C, what can you conclude about the population of people who shop at Paloma's Pet Palace? Yeah, I did create something that has 3 P's in a row. Pause the video now and go ahead and see if you can answer this question. All right, well, here we go, right? Somewhere. There we go. We can now conclude that the population of people who shop at Paloma's Pet Palace have a higher rate of cat ownership than the population as a whole, right? Now, again, how confident are we of that? We're 95% confident, right? And again, statisticians don't jump all over me for that, but that's the way I want you as a student to think about it at this level. There's still a chance, right? There's still a chance that I got that, 45% by pure sampling variability, right? That people who shop at Paloma's Pet Palace own cats at exactly the same rate, or not a significantly different rate than those of the population as a whole. But that's very unlikely to happen because, right, of where that sample proportion falls in this distribution. All right, and that's in marked contrast to our first exercise, where we found that even though Miss Amati's 86% was higher than the general population's 78% of people having brown eyes, it was too close to that 78%, given the sample size, to conclude that it was unusual, right? That in fact her students come from a population of people that generally have more brown eyes than the general population as a whole. Let's take a look at one last problem that is still concerning cat ownership. Exercise number 3. A telephone survey was conducted of adults in their 20s to determine if they own at least one cat as a pet. The survey contained 40 people and found that 6 of them owned at least one cat. Can you conclude that it is likely that adults in their 20s own cats at a lower rate than the population as a whole? Justify. All right, well, I'd like you to play around with this. All right, we already know what the plausible interval is. So pause the video now and see what you can figure out. Well, the first thing I have to do is I need to figure out what my sample proportion is, right? I know that of the 40 people, only 6 of them owned at least one cat. So my sample proportion in this case is 6 divided by 40, which ends up being a proportion of 0.15. Okay? So my sample proportion is 0.15. The question is that low enough? Is that out here enough for me to be able to conclude that they own cats at a lower rate? Well, let's take a look, right? Our interval is 0.117 to 0.389, right? So 0.117 to 0.389. Yeah, I guess I didn't put it on here. But, right, our 0.15 is actually right there, 0.15. Now, what that tells you, right, because the 0.15 is within this interval, it doesn't tell us that they don't own cats at a lower rate. It tells us that we can't definitively conclude that. In other words, the 0.15 is within a plausible interval where it could have happened by sampling variability alone. That could have happened, right? And therefore, let me put this up here. Although this sample proportion is lower than the population proportion, clearly, right, 0.15 compared to 0.253 or 254, right, even though it's lower, it still falls within the 95% interval, okay? This means we cannot conclude that adults in their 20s own cats at a lower rate because this sample proportion could plausibly have happened due to sampling variability instead of the induced variability of the people being in their 20s, right? Now again, researchers might suspect, oh, younger people aren't going to own pets as much as, let's say, older people, right? And then they do this study and they get, oh, if only 15% of these people owned cats, but in the population as a whole, 25.4%. Oh, so yeah, they own cats at a lower rate. Except, again, that could have happened by chance alone, right? Because it falls within 2 standard deviations of the proportion mean, all right? And that's, again, very tricky, right? We can't say for certain that they do have the same proportion, right? But we can certainly say that there's not enough evidence to say that they definitely have different proportions, okay? So if we're out here or out here, like we were in that Palomas Pet Palace, then we can say, all right, yeah, that's due to the treatment. But as soon as we're within the plausible interval, all we can say for certain is that there's not enough evidence to say that this thing was due to the people being in their 20s as opposed to just being some random sample, right, that really came from the overall population anyway. Okay, so let's wrap this up. In our last 2 lessons, we really looked at 2 very similar ideas. The idea that we had some population with either a known mean or a known proportion, and then we took a sample, right? And that sample had some kind of treatment right behind it, even if it was an informal treatment like Ms. Amati's students, right? And then we were able to look at those sample means or at those sample proportions and say, well, are they unusual enough to conclude that the mean or the proportion that we got from the sample actually came from a population that was different from the one that we were originally considering, right? And we can only say that, quote, for certain, if it lies more than 2 standard deviations away from the same simulated mean, whether it's the simulated mean proportion or the simulated mean of means, right? Doesn't really matter. We add 2 standard deviations, subtract 2 standard deviations from the mean of our simulation, and if our sample is outside of that, then we say it is due to the treatment and not due to sampling variability. All right, well, we're going to look at one more day of making inferences, and that will be our last lesson in Algebra 2. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.